Right now, all around you, there are billions of devices having secret conversations. Seriously, your watch, your car, maybe even the streetlights outside. We call this the Internet of Things, or IoT. And today, we're going to pull back the curtain and learn the secret language that makes it all work.
I mean, think about it. It really does feel like magic, doesn't it? Your speaker just starts playing a song, your watch somehow knows all your steps, a tiny sensor way out on a farm can report exactly how thirsty the soil is. So how does that actually happen? What's the invisible thread connecting these billions of little computers, letting them all work together?
Well, the answer isn't magic at all. It's something called a protocol. And a protocol is basically just a set of rules. It's a shared language that two devices agree on before they start talking. Without it, all their communication is just meaningless static. But with a protocol, that static turns into a perfectly coordinated symphony.
Okay, so let's say you're an engineer building a new smart device. Where do you even begin? Well, you start with the most fundamental choice of all. How is this thing physically going to connect to everything else? Is it going to be plugged in with a cable, or is it going to talk through the air? And right away, you're faced with a huge trade-off. If you go with the wired connection, like an Ethernet cable, you get blazing speed and rock-solid reliability. But it's stuck in one spot. Go wireless, and suddenly you have all the freedom in the world, like your smartphone, but you're giving up some of that speed, and you might have to worry about interference. That one decision, right at the start, shapes absolutely everything that device can do. All right, let's start small. Let's talk about the world right around us. Most of the IoT gadgets we use every day don't need to beam signals to a satellite. Nope, they just need to chat with your phone in your pocket or maybe a little hub in your living room. This is the world of short-range communication. These protocols are the real unsung heroes of our daily tech lives. They're designed with one main goal in mind: get the job done as efficiently as possible without completely draining a tiny battery. We're talking about the distance from your headphones to your phone or from a smart light switch to a bulb on the other side of the room.
So if we look here, you can see there are different tools for different jobs. You've got your classic Bluetooth, which is perfect for things that need a steady connection, like streaming music to your headphones. Then there's its cousin, Bluetooth Low Energy, or BLE. This is the secret sauce that lets your fitness tracker run for weeks on a tiny battery. And then there's something totally different, like Zigbee, which creates this cool mesh network. Basically, all your smart home devices can pass messages to each other, making the whole network more robust.
But here's a crucial point. Having a connection, a road like Bluetooth or Zigbee, that's only half the story. The devices still need a common language to actually send meaningful messages on that road, and that's where messaging protocols enter the picture. To make this easy, let's use a couple of simple analogies. Think of a protocol called MQTT as a sort of postal subscription service. You have a central hub that subscribes to a topic, say living room temperature. Then, a bunch of tiny sensors can publish their readings to that topic. It's super efficient for collecting data from lots of places at once. CoAP, on the other hand, is much simpler. It's more like sending a quick postcard. It's just a really light, fast way for one device to send a direct command to another, like, hey, turn on.
Okay, so we've got our personal space covered, but what about the things in the Internet of Things that are miles and miles apart? Now we're going to zoom way out and look at the protocols that connect entire cities or huge farms.
This is the world of LPWAN, which stands for Low Power Wide Area Network. The name really says it all, doesn't it? The whole goal here is to send tiny, little packets of data. We're not streaming video, we're talking about a single reading from a water meter or a GPS location over huge distances using a battery that has to last for years out in the middle of nowhere.
And the main players here each have their own specialty. You've got LoRa, which is the king of super long range. It's perfect for things like agriculture, where you might not have any cell service. Then you've got NB-IoT and LTE-M, which do something really clever. They just piggyback on the same cellular networks our phones already use. NB-IoT is perfect for sending tiny bits of data every now and then, like from a smart parking meter. LTE-M gives you a little more bandwidth, so it's great for things like tracking a valuable asset as it moves across the country.
So, we've just thrown a whole alphabet soup of acronyms at you, right? Zigbee, MQTT, LoRa, NB-IoT. How does anybody actually choose the right one? Well, it turns out you can boil this entire complex world down to a really simple and powerful framework.
This is it. This is the key takeaway. It all comes down to asking just 3 simple questions. First, range. How far does the signal need to go? Are we talking feet or are we talking miles? Second, power.
Is the device plugged into a wall, or does it have to survive for 5 years on a little coin battery? And third, bandwidth. How much data are we actually sending? Is it a simple on or off command, or is it a continuous stream of information?
And that's the whole game. Every single connected device on the planet is the result of a carefully balanced trade-off between those three things. You simply can't have it all. You can't have a device that sends tons of data over huge distances while using almost no power. It's impossible. The real engineering genius is always in finding that perfect balance for the specific problem you're trying to solve.
Which brings us to this final, really important idea. There is no such thing as the best protocol. There's no winner. There's only the right protocol for the job. It's like asking what the best tool is. Well, a hammer is fantastic for a nail, but it's a terrible choice for a screw. The language a smart water meter uses is perfect for its task, but it would be awful for your headphones, and vice versa. It's all about fitting the tool to the task.
So the next time your smartwatch sings or smart light turns on, you'll know it's not magic. It's just a series of really clever choices balancing range, power, and data. And that leaves us with a pretty cool question to think about. As our world gets more and more connected, what new problems are we going to face? And what new secret languages will our devices need to invent to solve them?